Okay.
Is it still sharing its screen?
Yes. Yes. So can you guys see the screen that shows the FreeSurfer this first slide?
Yes.
Okay. Okay. And another thing I want to mention is that when I'm going to go over here, there are a couple of spots where it's specific to Suen's pediatric data. So there's a few different things we do for pre-processing. That's not going to be a highlight here, but just know that maybe some of the commands that there are a couple of commands up there that may change a bit from here. Okay, so some background. So we use FreeSurfer to first segment out the gray and white matter structures on a brain. Just as actually I think even a step back. So this is one slice through a T1 structural volume of brain scan. And what we use FreeSurfer to do is to identify what's the brain in here. So on this slice, this is a pretty good job of identifying what's the brain. And then we want to determine what is gray here, the cortex. Sorry, we have a technical malfunction. Oh, okay, here we go. Okay, so what's the cortex here, this gray strip? And really from just about everything else. And that's what's on this slice here, where you see the everything else part of this, which is known as what will be called the white matter volume, is the white matter and then some subcortical structures in here. So we're really trying to segment out this stuff from this stuff here. And once we do that, then we're going to build these reconstructions of the cortical, of the peel surface, the outer surface of the brain, and the white matter surface. And actually what we do is we first get the white matter surface here, that's what's in blue, and then that is used to determine this outer surface here. So what our job here, when we run the recon-all process, is to assess how good a job it did of doing the segmentation in these surfaces. So just as another little background point, when you run the recon-all process here for a subject, so this is the subject's name, this says you want to do all the recon from the start to the finish. This is a pointer to what the source data are. So this is the source anatomical volume. This bit here in bold italics is the piece that's specific for Suen's pediatric data, where we have this custom pediatric volume atlas that we use as part of the pre-processing steps. And here are a couple of additional parameters that are specific to the kinds of images that we're collecting. That's actually similar to the two groups. When you do that, you get a subject's data directory. So I don't know if one thing that you may or may not have already gone over is that one really important environment variable when you log into your system and you go to and you're looking for the data is this variable subject's dir. So this is FreeSurfer uses this when it calls different commands in its from its software suite. It looks for this destination, so that'll be like on your computer, it'd be something like /data2/FreeSurfer2/ and then it'll be some subject ID here. In that directory, the recon-all process creates a bunch of additional directories, and these first four here are the ones that we're going to be specifically interested in for the review and editing process. These other ones here are also very important, but we're not going to be, they're not relevant for what we're going to go over. These first two are particularly relevant because that's where we find the files that we want to edit and assess. So in MRI here, that directory will have all of the data volume files that are in the FreeSurfer pipeline. So that'll be that initial T1, the original one, and it'll also include all the volumes that are derived from that. So you correct it, you do some normalization, intensity normalization, and you have various masks. So all those volume files will be found in that directory. And in particular, we'll go over a couple in the next few slides, the two that we're going to be spending most of our time viewing and editing. The next directory is also very important because that's the surf directory. And so that's where, when FreeSurfer creates these surfaces that we use for all sorts of different analyses down the road, all the surfaces are saved in the surf directory. And we are going to be focused on a few specific ones there. We don't actually edit the surfaces themselves. We look at them, we determine how good they are, and then we edit the volumes to actually improve the surfaces. The next one doesn't seem like it's important given the name, but for whatever reason, that's where the FreeSurfer group decided to store this a very important file that includes these control points. So we'll go over what those are. They are an important tool in trying to improve the FreeSurfer process. And then this last one here that's in bold, the scripts directory, here's where the FreeSurfer pipeline stores a number of text log files that have information about what's been run on this particular subject and what versions of the software were used, when it was done, and also importantly, what errors were encountered. So those are ones that you want to be familiar with. Okay, so we run recon, we have these directories populated. Then we want to review the output and potentially do some edits. So what the goal of the process is to identify in each subject errors in segmentation of the T1 volumes and the cortical surface reconstructions. And we want to determine if whether those errors can and should be corrected. So I would say for SUEN's pediatric data, because it's kids and kids move around, pretty much every volume is going to could use some correction. Some may be so minor that you just say, look, this is better than the other one. I'm not going to spend my time doing this, because when you make an edit, you make the edit, then you have to run recon, and then you have to review it again. Turns out that you can make edits to make things worse. And a big part of the learning process here is determining when that's likely to happen, and then avoiding that waste of time. So you're going to, just about every volume is going to need or could use some correction. A key decision to make here for this data set in particular is whether or not the errors that you see can be corrected. Can they be corrected? Is it worth your time to correct them? And why is that particularly important in this set, in this data set? Well, it's because they're kids that move around a lot, and when you have a lot of movement, it can reduce the quality of the T1 scan to the point where really there's not much that you can do from an editing standpoint. And then you're left to try to find other ways of trying to salvage the data that we won't go over today, but that perhaps we could explore down the road. And then if you determine that, okay, there are some errors here, I think we can correct them. I think it's worth the time that it'll take to correct them, because all this data, they're all very valuable. Then you have to go ahead and correct them. So we'll go through this bit. So what we want to do is review the following files to make these decisions. And the first one is one that I showed you a couple slides ago. It's this volume that's in the MRI directory called brainmask.mgz. And that's a pre-processed T1 volume with most non-brain voxels removed. So the idea is that they've stripped away the skull that was around here and a lot of the bone that's down here and other tissue. It's not perfect, so you still see some voxels that are outside the brain left behind. And in this case, it does a pretty good job. You see a little bit of tissue up here too. When it looks, this scan is fairly high quality, so often the processing steps that come downstream from this are able to understand that this is outside the brain, and it will make a surface that does not include these things in it. The other thing that it does here, which is key for those of us that want to try to figure out ways to improve the core scans, is it tries to do a normalization step on the white matter. I'm sorry, on the gray and white matter intensity. So it tries to find what it thinks is white matter, like an initial attempt at what it thinks is white matter, and then it tries to normalize that white matter intensity to a single value where it can. So this, if you're familiar with looking at T1 volumes that come right off the scanner, they're not nearly this. They're not nearly this. The intensity isn't this blotchy and uniform, and that's actually a very important step, and is really good when is very handy when the data quality is pretty good. It's not so good when the data quality is bad. So you can get things like it can pop up and make really high intensities for some white matter in some places and not in other places. And we'll see some examples of that.
Jason, did you say that it normalizes both? It tries to make the white the same intensity and the gray the same intensity?
It tries to I believe it tries to normalize them both. And so one concept that will be important as we go forward is this idea of gray-white contrast. So it's how easily distinguishable is the tissue that is white matter, so this tissue here, from the gray matter, this tissue here. So right here, this boundary is pretty distinct. But when you get into here, you see these little bands here? Those bands there are a sign of some movement. And this is actually a pretty good scan. But the distinction isn't quite as clear here. And here you would say that there's not a sharp transition from gray to white here. I'll just want to stop for now and just make sure, can everybody see the slides, and can they see me poking around with the cursor?
Yes, we can't really see the movement lines, but we believe you that they're there.
Well, I missed that.
So they know what movement bands look like.
Oh, Emily, we're having a hard time hearing you.
Sorry, can you hear me now?
A little better.
That's weird. Let me see.
Oh, that's.
Is that better or worse?
That's better. Yeah.
Okay, sorry. Yes, we can see the screen. We can't really see the movement bands, but I've shown them pictures of what that looks like, so they're all aware.
Yeah,
Okay.
this is very subtle.
Very subtle.
Yeah.
We'll have more brains later that.
Yes, I showed them some pretty terrible ones. So.
Okay.
Yeah.
Excellent. Okay, so and we're going to make some we may be editing this volume or removing some of the extraneous voxels that are not in the brain. And I just want to short shrift this other volume that we are interested in this presentation. It's in that document, and we'll talk about it more in a future visit. But if you have an area and where, so I guess like I said, brainstem, but the more commonplace is cerebellum, where you have something that is not within the cerebrum here, but is immediately adjacent to it, and you have a surface that jumps into that other brain area. If you were to erase that from the brainmask.mgz volume, those voxels would be basically eliminated from the brain. So it's as though that tissue didn't exist in the brain. We don't want to do that. So there's this other brain volume just for that one special case where you would edit these. So when you erase something from this, it is erased from what FreeSurfer will consider cortex, but it won't erase it from the brain itself. So if you there's another segmentation step that really isn't all that relevant here, but where you get a cerebellum, you don't want to delete those voxels, so it'll you use this by editing here. They'll remain for that segmented area. All right, so here this dark blue is kind of hard to see, but this is what you get the labeled tissue in the white matter.mgz volume. So this is meant to be, or everything in here that's got a value that's greater than 1 is considered white matter, but I put that in parentheses because it's not really white matter. It's really subcortical tissue of the cerebrum, as I mentioned before. So it's not cortex. think of it that way, and it includes things like the ventricles and the thalamus. This volume here, which is derived from the T1, is very important because that's the one that is used to build the white matter surface. So I'm going to transition from here to here, where this is the white matter surface that's built from this labeled volume, and it uses the labeled volume as a guide, but it's not just the labeled volume. And to be honest, it's still a little bit mysterious to me exactly how this is come up. But they use templates, and and I think they use so basically the number one, the highest priority for defining it is what is labeled white matter in the white matter segmentation step. What's in here, this white matter.mgz volume. But an average template and tissue probabilities also plays a role, and that is actually going to be, you'll see this distinction will become very clear because when you want to improve this surface, here it's a pretty darn good surface. It doesn't need a whole lot of improvement, at least on this slice. We will make edits to the white matter.mgz volume, and we may add these control points that I mentioned, and they will have a not quite deterministic effect. So they will kind of nudge things hopefully in the right direction as long as we're doing a good job, but they won't necessarily make things exactly like what we want. And that's so that's really the biggest part of the learning process is what edits are worth you trying to make. That white matter surface here, once we have this, the next step that FreeSurfer does is to go from points all along that surface, and it marches out from that surface into the cortex, all through here, and based on a few different constraints, including how much the intensity can change from this point at the gray-white interface to into the cortex, distance and limitations on whether or not you can have crossing points. It builds this peel surface here. So its peel surface is basically, that's what FreeSurfer considers the most the external limit of the cortex, and that's here in the yellow. Let's see if there are notes here. It's determined primarily by the white matter. A few more caveats. Most peel surface errors that are not due to a white surface error are correctable. So that sort of goes back to this. If you notice that the peel surface is, I think this has been corrected, but let's say the peel surface incorrectly included this little piece of duramatter or vessel here. If you just erase that, it's deterministic. The surface will not continue on to that point. So that's a distinction to make here is, well, actually, I'll leave that. I don't want to jump ahead. So, are there any questions here?
If you make edits to the volume, will those affect both the white surface and the peel surface, or depending on what you do, can you isolate it to just affect one but not the other? You can, so if you were to say edit like erase some things here, like if this popped out here, if you were to edit this, it would have no effect on the white matter surface. Right.
I believe you could if you erased a bunch of stuff, yes. If you erased all of this, and there are occasionally you have an error where you would erase some white matter, right? Or yeah, you would erase some white matter in the white matter volume. It would affect both surfaces. So if FreeSurfer makes a mistake, say in labeling the white matter. So if it labels something with white matter, it's not really white matter. Yeah. And so the way to think of it though is if you change the white matter segmentation, it will affect both the white matter and the peel surfaces. If you change the brain mask, that will change that. And you do it in a way that's not purposely trying to ruin stuff, right? So you're just getting rid of non-brain. That will generally only affect peel surface. But with in most cases, so we have a few of our ACE pediatric scans where there are some problems with kids moving around, and we can do some corrections there. But you'll see with the motion is more widespread because Suen got kids that are down to under 4 years old. You're mainly the main issues you're going to have are in trying to fix that white matter volume, the white matter segmentation, to try to improve its labeling of the white matter. Okay, so this is a quick aside, a protocol note that says, okay, we're looking here. Before we do any reviewing of or editing of data, so not just before editing, but also just reviewing the scan, it's important that we make a copy of the files that we're going to look at. So we're going to be looking at these 4 files, these volumes, and there will be a couple of other files that we'll look at. We want to make sure that we have and then the idea is that potentially down the road we're going to be editing and regenerating them. We want to have a copy of them. So we want to have a copy of the surfaces from that previous recon, and we want to have a copy of the volumes of them. And that's for a couple of reasons. One, it makes it easier well, the main reason is it makes it easier for you to track what's going on. So you make a correction, and you want to know what its effect is. So you want to have those. You're going to run recon again. You'll have the new surfaces. You can just want to overlay them on the old surfaces, and you can say, okay, it looks a lot better, or it doesn't look a lot better. Maybe it's even worse. So it makes it much easier to understand to understand what the effect of any error is. It's also good. It's good. It's particularly early on when Bobby and I will be interacting with you, so that we can understand what you did. So we can say, okay, this is what this happened here. Let's propagate this through. Because on some scans you might recon 5 or 6 times.
It's rare, but it can happen.
It can happen, and it's nice to see what. So especially when we get to talking about control points later, those control points don't just they affect things more globally, and sometimes, especially even if you are very, very experienced with them, can have unintended consequences, and you want to know where along the way that happens. So it's very important that before you do any data review, after you run recon, before you look at the scans, that you copy them. And we have these scripts that we've created. Oh, actually, before I got to take a step back. Even before you copy them, you want to make sure the actual first thing that you want to do, is to make sure that recon finished and is without error. So you can just go to the subjects directory, and you can run. There are a number of ways to do this, but one of the ways is to just look at this recon all. So in the scripts directory, there's a file called recon-all-status.log, and you can look at the last line, and it should say something like recon all finished without error. There's another file that has a lot more detail called recon-all.log, which basically is the output for all the free surfer processing on a scan. And if you use the command tail, T-A-I-L, instead of cat here, and to view that file in your terminal, that'll give you the last few lines. You can see, let's say, finished without error. And the nice thing there is it'll also tell you it'll tell you about the error if one did occur. So you want to make sure that the recon all process finished, and then it finished without an error. If there was an error, you'll have to investigate and try to figure out what went wrong. And then, early on, I would say you just email Bobby. Does that seem good?
Yep, and
Okay.
I will look into it.
Okay. So then the next thing that you want to do is copy. The next thing you want to do. Man, I really missed the boat on this one.
Sorry, I was
Sorry.
staring right at it too.
No. Okay. So the next thing you'd want to do is but this does lead up. It's good to know that you need to copy them. You want to know how many recons have been done. So so one way to do that is just to list all of the files. So one of the files that we edit a lot is the whitematter.mgz file. So you can just list, so ls, you're in the subject, the free surfer subjects data directory. You list for this subject A, and this is, so let's say, skip the ACE here, it's just 9048/MRI, that's the volume directory. Then whitematter star, that lists all the files in there that, that start with the letters WM, and then we can look and see, okay, here's the whitematter.mgz volume from the most recent recon process, and then we have a recon 1, and a recon 2, and a recon 3 here, and a recon 4. Already 4 on this one. So what this means is that FreeSurfer, the recon has been run 5 times, including the most recent one. So what we want to do now is make a copy of the relevant files that we will edit and could change based on our edits. So what we'll want to do is use this script and the location of this script sort of jumps around. I think this I think the way that you have it as a default is that in your FreeSurfer subjects directory, there's a directory called scripts, and in there you have these scripts that are useful. So you do something like // and then scripts / this bash shell script, and then what you do is you give it the subject ID. So when we work with the data, we just use these four numbers. Whatever happens, we have to, if you work it with it where it's like SF underscore something or whatever, you put that there, and then here is the number of the recon. So if it's the very first one, if you reconned it for the first time and you're just doing the initial review, you just put a 1 here. That'll make all those files underscore recon 1, the copies. In the case of this example that we looked at here, we'd put a 5 there. Okay.
So it's not what it says recon 1, it's actually you count because the first one doesn't have a tag.
The first one, so
The first one's just W.
you basically want to pick the next number that's available. So if it's recon 4 here, you want it to be a 5.
Oh.
So WMMGC is the most current view of.
Oh, and the other
Yep.
ones are the recons.
Yes.
Right, so recon, whitematter underscore recon 1 here is the original one. And then recon 2 here is after you did some edits. And then recon 3 is after you did some more edits. And recon 4 is after you did some more. And then after you did those, you have whitematter MGC here.
So it's always output as
Just
Right.
W.
And this is
Yeah.
this FS recon, this is something I did. Okay, so this is not FreeSurfer standard. This is just as we start to do this on a grander scale, it really is key to be able to see what the changes were based on the edits. And you'll notice that we have this other thing. We'll talk about this later, probably, or maybe next time. This underscore edit 1 here. So those are the edits that were made to files that were generated with the first recon 1. So we had recon 1 files, and then we edited them and saved them with edit 1. Then edit 1, those files are used in the recon all process to make whitematter recon 2, and then we have whitematter edit 2 after we did some edits, and then those are used for recon 3, and so on and so forth.
So that's just the processing steps, or like whatever the edit steps were.
Right. It's just basically keeping a copy of all these files. I mean, there are tons and tons and tons of files that are generated, and we use a lot of them. But for the review editing process, we limited them to these. Let's see. So it creates a whitematter. Copies of the whitematter volume, the white and peel surfaces, the brain mask and MGZ volume, this brain final surfs man edit volume that again we're going to just give short shrift to today, and the control.dat file. And actually, this is I gotta fix that. That shouldn't be TMP. Okay. Okay. So you made the copies. Now we're gonna want to review a scan. So the GUI that we use for that, and I think you guys are all familiar with it in Michigan, is the Freeview tool. So we have another script that may be helpful, which is called BFVO new, which is really poorly named. Really poorly named, but so it goes. We have to change a lot of help documents if we change that. But this is also something that we came up with, so that what it does is load all of these files for you in one relatively easy command. So if, let's say, you were just going to load one subject's worth of data, that would be, you'd have to run Freeview. This VGL run is actually, this is familiar to on both ends here, where that you have to run that if you're using one of these VGL remote servers to do the to look at the data. You'd have to type in this -v means volume, and if this volume, this volume, this volume, this volume, that sets the color map to something, so it's easy to see, so it's easy to distinguish volumes that are laying on top of each other, all these surfaces and everything. So what this does, and this is just for one subject, and the recon files from one recon. What this will allow you to do is to load up, by just typing in a subject's ID here, it's going to load up the most recent recon files. It's also going to load up, if you give it another input here, it's going to load up the files that have this suffix, so _recon1. And there have been times when I've even wanted to overlay 3 different sets of files, and you can put one more here. So it could be like, so occasionally I want the most recent, I want the original, and then maybe I want my last edit, so I could just be a reminder of my edit, so I can put edit 1 here, and it would do that. It would look that.
Want to look at the most recent? You would just do the subject.
Just skip this.
Okay.
You just skip this. And I find that the only time I want to do that is if I'm looking at the scan for the first time, basically if it hasn't been edited before. If it's been edited, I almost always want to see what those edits are. If my goal is to assess the paint. Okay, so we run this on this subject 4043, and here's what the FreeSurfer interface looks like. So the arrangement of this is just basically based on what it was the last time you loaded it, and for review purposes, typically we have the coronal. We'll be doing, that's where most of our work is done, and that'll be nice highlighted here. But you can arrange this in different ways, and it loads up the brain mask. So one of the things that it doesn't do is actually load up. It doesn't load up the brain mask from the original by default, and you can change that. So everybody is welcome to modify that script as they like and make their own version of it. So BFVO _new was Bobby's Freeview open _new, the new version of it, and so it's customized for her.
Why would you want to load up the originals? Like check your edits again?
It's to see how much improvement there's been,
and
so
to see if there's been any errors made.
Yeah. And you might not want, so you wouldn't always want to look at recon like the original say. Often you want to look at the previous one. So if you're looking at the one that we looked at that already had 4, I'd probably load up the most recent one and recon 4 to see what effect my most recent edits made. Okay. It will. So for you, you have Bobby here. So I don't know how deep into the edits you're going to get. So you may just want to be assessing, like out of the gates, oh, something went terribly wrong here. We got to figure this out. Or not terribly wrong, but something not right. Basically assessing. We got to do something manually before we can move on to analysis. If that's so, this may not be as relevant for you. But if you're going to do edits, if you want to get into that level of detail, this becomes pretty key, especially, and as I was saying, especially for at the early stages here. But I use it all the time. So we started doing this for Suen, and it's a lot of scans, and we once we went from just trying to get a sense of what we need to do to ramping up to like production level, where you're trying to get a lot done fast. This became a really just almost like, yeah, not even just useful, but necessary to keep track of what's going on. Okay, so what you have when we load this up, you see these three views: coronal, sagittal, axial, and then here is the 3D volume. So what I did here is I just turned off by unchecking these boxes here. You don't see the originals over here overlaid. You only see the most recent, and that's so that you can kind of make heads or tails of what this is here. Okay, so when we do the review procedure, we're trying to do things as rapidly as possible, but being conscientious. And we've tried to break things down into a few steps. So what you want to do this very fast initial assessment of the brain. And one of the things you can do is to just quickly look at 3D surface here, and you can get a sense of how of the quality of the surface reconstruction just by looking at that. So if you look at this top row here, this is a lateral view of the right hemisphere, and here's a top-down view here. You can see in this scan that the gyri seem relatively full, and you see relatively little red here. So the green-red here is basically surface curvature. So the green is indicating gyri, and red are sulci. So you see there are these tertiary sulci, these really small minor sulci, where you see some red exposure, but it's relatively small. If you contrast that to a scan down here, I should say that and the surface is relatively smooth too. If you look down here, you see a lot of bumps here, like I guess kind of more jagged edges. You see a lot more red, so the sulci are exposed. You see things like here, so here's a typical looking temporal lobe where it comes down and it's nice and round. Here it's truncated. It doesn't extend as far forward as it should, and it's jagged. So if you were to look at the coronal slices of this, you'd see like, oh, there are a few slices at the anterior portion of the temporal lobe that are just cut out. And if you look from top down, again, you see some of these kind of odd bumps. This is a sign that the recon did not do very well here.
So then you just go back a step. Right?
Well, so what I would do is that's actually like assessment 1, so 2 we'll call it. So assessment 1 is, does this look good or not? Assessment 2 is, why does it not look good if it doesn't? And in doing that, you'd want to take a quick scan. So when we're actually doing the editing, you're looking through every slice. You're looking through every slice and taking this. We want to kind of skip around a bit and just go through the coronal slice series, or well, not just the coronal, all the slice series that we need to, and determine if the errors that we see, and really these errors actually probably going to pop up on here too, are a global free surfer processing error. So you can have an error where like the normalization of the scan is really bad, and that could be because somehow like a dimension was flipped, like left-right was misassigned, or what free surfer is expecting as the x dimension is really the y dimension, and you're just going to see gobbledygook. It's not going to look like a brain at all. Other things that can go wrong are skull stripping. So there could be some scans where free surfer just does a really horrible job of the skull strip, and that causes problems down the line and the need for a lot of errors. There can be an intensity normalization problem, and Free Surfer's wiki has examples of this. I think we have a doc that has some examples that we've shared. Maybe we could stick that at the end of the pediatric edits doc. has some examples of this. But when you look at them, it's not going to look, it's going to look like a complete mess. It's not going to look like you're going to see large scale errors that are global, so they're affecting the whole brain. When you see those errors, you should not address them with manual edits. So that'd be something like, as Megan brought up, something where you may have to rerun FreeSurfer with a different parameter settings. So you can there's a parameter that determines how aggressive the skull strip will be, or you may find that I need to reorient my input data because there's some sort of problem with it. Those are ones where you're not doing manual edits. And for you guys in Michigan, if you see this, at least for the time being, if you see some really messy data, just alert Emily and Bobby, and we'll take a look at it and see what we can do to fix it. Okay. If you don't see a global processing error, so like something like this isn't really is probably not a global processing error. If it was something like a bad skull strip, the bumps would be even more prominent, like a lot more bumps. If it was a normalization issue, you would think it'd be like pieces of this would be completely lopped off, or look like it was upside down and inverted on itself. If there's no global processing error, you want to assess the general segmentation and surface quality to determine whether manual edits can improve the surface. So it should take, within a matter of seconds, you say, oh, global processing error, email Emily, email Bobby. In the seconds, the few seconds after that, if you decide that's not the case, you want to, as you go through, I mean, these things don't have to be independent of one another, right? You can do this assessment along with the previous one. You want to determine if you know that there are errors, and maybe there are a lot of errors, like on that example we saw up here, can I fix those errors with manual edits? And on some portion of Suwon's data, what is it, 10, 13%?
Yeah, 13%.
13%. We've determined that no, you can't. It's just not, there are problems with it. So even if it's not a FreeSurfer error per se, the quality of the data is just so poor that there's really not anything that we're going to do with manual edits or a FreeSurfer parameter tweak that's going to fix it. So, and we've just recently started to discuss what we can do to fix the scan. So here's a good example of one where it's not a global processing error, but this whole lateral surface here is a mess. It's basically kind of chopped off, and you can see that. So here's the T1 of the brain mass scan, and you can look, if you look over here, I guess it's not very bright, but the outline of the cortex is over here, all along here. So it's basically, it's not picking up any of this, and this is across this from anterior to posterior in the on the left hemisphere. So
It's the right.
it's right. Okay.
And you can see the difference in the intensity of the gray matter
Right.
from left to right.
Right. So what you can see here is this gray matter. This is gray here. This intensity is much lower than it is over here on the left. And so, and because of that, so because FreeSurfer has these limit when it goes from the white matter surface out to the peel surface, it has some constraints on how much it can change, how much the intensity can change. Because in most brains, if it changes a certain amount, it's outside the brain. It's no longer in the cortex. So because of this, you get this major error, and there's really nothing that we can do to fix that using FreeSurfer tools or manual edits that I'm aware of. What you would need to do is manually increase or so normalize the cortical tissue intensity here. Okay. This is just continuing with this. Before beginning manual edits, it's important to quickly assess whether the time and effort is likely to significantly and sufficiently improve surface quality. I guess this is actually not just repeating it, except it adds a little bit of information. So you want to quickly review the peel and white matter surfaces overlaid on the brain mask and white matter volumes to look for erroneous exclusion. So this would be a major exclusion area error here, or inclusion errors of cortical voxels. And in particular, in this case, what you want to look for, ones that are not local isolate problems. Like local isolate problems are usually pretty fixable. But if it's a major regional problem or a global problem, that's one. So here I'll just read through this, talking about the major types of error classification, because you can sort of break down what you're going to do in terms of edits by whether or not it's an inclusion error. So non-cortical voxel that's incorrectly included between the white matter and peel surfaces and is therefore erroneously treated as cortex. These typically arise from duramatter and blood vessels that lie along the cortical surface and an incomplete skull stripping. Less commonly, they will result from peel surface extending past the cortical surface into adjacent brain voxels. We talked about that a little bit. There's a special way to fix that. Also, less commonly, they may result from voxels being erroneously labeled as cerebral white matter in the white matter volume. Exclusion errors, where oh, I think I must have grabbed the wrong thing here. But exclusion error is referring to the omission of voxels that are cortical tissue between those two surfaces. So like we had here. So you're lopping this off. I think I've just grabbed the wrong paragraph here, but I'll just mention this while it's up here. So you see that most prominently near the lobe poles, particularly near the temporal pole. And the most common source for this are going to be intensity drift or fall off and motion, which results in poor gray-white contrast. So the white matter, like stuff that's white matter, is a little dark, looks more like gray matter. The white matter is not labeled in that area, and therefore it doesn't grab the cortex that surrounds that white matter. Here's an example of an inclusion error. A very common inclusion errors that are the ones that are local or regional and that can be fixed with manual edits. So here we have duramatter that's right along the surface of the cortex here. And in red, if you can see that the red here, this is the original recon surface, extends out there to include that. Here's another very common spot for inclusion. This is a blood vessel that goes along here, and the peel surface will extend out. Exclusion errors. Here's one where it's basically just lopping off, and this is somewhat surprising because the overall quality of the scan is okay. You see there's a little bit of banding here that you may not be able to see, so the contrast isn't perfect, but you can see these white matter fingers here. This is Heschel's gyrus, primary auditory cortex here, superior temporal gyrus that's nearby, planum temporal here. So this area is huge. So it's one of the top two most important areas for us that we want to be accurate. This, and I would say like inferior frontal gyrus and premotor cortex. So this area here, what you notice is that this gray here looks pretty good match to the intensity throughout the brain right down here. But then this gray is really dark, and this gray is really dark, and then this gray is really dark. And for whatever reason, FreeSurfer is not labeling these bits as white matter, and all this gets chopped off. So we want to correct that. Especially, so if this was a scan that had a ton of motion, it would look really bad, and there were global problems throughout, you might say, well, this is not worth the effort. But this is regional. So it's not just one little gyrus that's lopped off. It's bigger than that, so it's going to take some effort to try to fix this, but it's worth trying to do it. And here's another. Is this a different scan?
That's a different scan.
Yeah. So here, this is something similar where the white matter volume is overlaid, and you can see that even here, there's actually blue there. So that was labeled in the segmentation stage as white matter, but FreeSurfer, for whatever reason, did not continue the surface out there. So that's where the mystery comes in. Okay, so when you're doing this quick initial assessment, which is, I'll contrast that with my quick initial description of it, which is not quick at all, taking up more time than I had thought, but I think it's useful background information. You tell me if you don't. But to do that initial assessment, it can be useful both for yourself and certainly useful for during the training phase. And it's actually, I think, very useful for tracking data quality control. So one of the things that's been important for us to try to determine how much time and effort do we want to spend on these brains is determine, okay, if we spend this amount of time, how many brains do we just eliminate, right? And so if you can make a rating of the scan and the surface reconstruction quality as you go through here, it helps us both in terms of your learning and in terms of us trying to determine what's the best approach here. And the key here, I meant to highlight these, but I didn't, is between 1 and 2. So we would give, if you're looking at a brain, you give it a 1 if the cortical reconstruction is very poor and you're likely unable to edit it sufficiently. Sufficiently with manual intervention. And this isn't, so I'm calling this a rating of the reconstruction, but it's really a function of both the reconstruction and the T1. And I know that, Emily, that in the past, and we continue to do so, I found that it was a little bit confusing to have both here. We have a rating for the T1s, the volume, the data itself, the volumes, and then a rating for the reconstructions. The two are kind of tightly intertwined. So here I'm just focusing on the reconstruction rating, but the idea is if you have a lot of errors but the scan looks great, it's well, okay, well, I can probably, there's some potential for me to fix this. If you have a bunch of errors and the scan looks terrible, then you don't. Then you might not, it might not be worth the effort. So it's sort of tied into this rating. A rating of 1 means you don't think it's going to be, we can fix it to a sufficient level of quality, and it's unusable. And I've Emily, here we've labeled what you've been using as a rating system, and then just stuck our BU definitions, which as usual are more wordy, whether or not that's necessary. They're more wordy, and you see that they're essentially the same thing, except that you have this magical doesn't need an edit rating that we just skipped. But I like that. I like the idea. It gives hope.
Much more optimistic than we are.
Yeah,
This
I like it.
5.
That's fine.
Oh, I think we're missing. I'm having a hard time hearing you again, but
I'm so close. I don't know why it doesn't work.
No.
very local microphone.
Yeah.
So, yeah.
All I was going to say is a 5, we don't usually find them. It's just, we wanted to have a 5 just so that, as an example of teaching the students that this is as good as it's going to get, basically.
Yep.
It's not perfect, but.
That's fine. That's fine. It is true, I think that you'll always find some things to fix, but there have been,
Right.
So especially with our adult data that we're collecting, you can find a scan where you can say, well, I could fix this, but it's not worth it. It's just not worth the time, so you wouldn't edit it.
Right.
Yeah. So the big distinction here is between 1 and 2. So 1 is we're not going to use it, and if you find that, don't just not use it. We have these reporting spreadsheets. You're going to be putting that in there, but email that to Bobby or me, Emily. Let us know when you find a scan that you think is unusable. then number 2 is it's not, the recon's pretty poor, but I think we can salvage it. So manual edits and the volume edits and the control points are necessary, and maybe even a lot of them. But if we put the time in, we can salvage that scan. We can get it to sufficient quality for doing analyses. So that's really the key here, is the 1 and the 2. Then a 3 here is it's okay. It's an okay recon, but it's going to require a moderate amount of volume edits and maybe some control points. And then 4 is it's good. It's a good recon. You need to do some minor volume edits. So the errors are highly local. You know, they're on like a few adjacent slices, and then you're going to be in good shape. And then, again, as we said, 5 here is the doesn't need to be edited. We can just close the book on it. Go ahead.
Emily, I just wanted to ask you, I'm looking at the time. Do you guys need to go?
We only have this room until 12:45.
Okay, 12:45.
Okay, so what I think we're almost to this. We're going to look at some examples of these, and then are we meeting again next Thursday, or is that when there's a break?
I believe so. MSU people, next Thursday is only Erica can't be there, right? Okay. Yeah. So on the 17th, none of MSU people can come, so we can skip that one. But yes, next week we can still meet.
So Thursday. So people will be around on Thursday.
Emily, we couldn't hear you. Could you say that again?
I couldn't hear you either. I think we're
Sorry.
all.
Hello.
Yeah, there you go.
Okay. So I'm just confirming. We're basically going to meet every Thursday, except on the 17th, none of the MSU people can be there, so we're not meeting. Next week on the 10th, Erica can't be there, but the other 4 of us can, so they can catch her up.
Okay.
That sounds good to us.
Okay. Yeah, there's some times later in June when some of the MSU people will be gone, but we should have a few before that.
We won't need that many. We'll go through this PowerPoint in the next, probably in the next meeting. And then I'll go through, maybe one more week of just not even with our people, but just with you guys, opening up a brain and doing it live.
Okay.
And send them off on a training brain, and then they can write to me as they need.
Okay, great.
Okay, so what we'll do, we'll go through some of the examples, and then we'll save for next time the sit down how-to stuff.
Okay,
yeah. Okay, so here's an example of one that we rated 1. So if you look at this scan, you see look, the banding here. See this banding here that's indicating motion, and it's kind of blotchy. So you see motion artifact. There's inconsistent gray-white. So like right here, the gray-white boundary contrast is poor. You see that the intensity of the cortex over here really falls off. And when you look at the cortical reconstruction, the white matter here is actually it's okay. And some of the stuff, like the poor quality here, is actually there's probably some more white matter here that you just not seeing here. But the peel surface is a mess, and this is really the most difficult thing to fix. Because we don't have a way to just manually fix the peel. Go bigger, peel. I'm not aware of a way to do that. And so when you have something like this, there's not a good place for us to make edits. So how do we make the white? So the way to make the peel bigger, right? So to fix an exclusion error that you see here is to make the white matter bigger, to make more white matter, or more voxels labeled white matter, and there's not a real good way to do it. Like you could probably fix a little bit here. There might be a place where we could do something, but given the scan quality, this is a little bit more interior, where the gray-white contrast is even worse. And you see one of the things that's not all that prominent here, I'm sure we'll see one at some point, is when you have a lot of motion, you'll see like these, like this gets dark here, but then it gets bright again. So this is not white matter out here, as far as I think. I think it's not, but it's bright. So it becomes really difficult to determine. So we would say this one, just forget it. You know, just forget it. Okay. Now we move on to an example of something rated 2, where here it's even easier to see, I think, the motion artifact going through here. And you can see the banding. So like, here's a nice example of this band where this right here is just, everything's just darker, right? So it's very confusing for a free surfer try to know what to do with this. So here's that slice where we're looking at the recons here. And actually this one showed, I think this one.
That's
No. Is this the same slice?
No, it's not.
Okay. Okay, so this is just showing that, okay, if you get something like this, you get a recon here. Is this the,
That's the original.
this is the original?
Yes.
Okay. So this one, it'd be nice to see what this one looks like, but we can, is that what this is? No.
That one's the same as the middle one, but with the recon.
Okay.
Sorry.
Okay. Well, that's a fair, I mean, this is like, so, well, here's one, but that's just more like a local thing showing just evidence that you can make these things better. But this surface is, when you look at this surface here is really tight. So like this is all cortex here, all around here, it's just underestimating it. You could probably come up with another 2. It's going to be more clear, like what kind of errors you get, but it's something where it's kind of messy, but we can fix it. Here's one that was rated a 3. So when you look at this one, there's a little bit of evidence of motion here, around here. And you see like over here, the gray-white contrast isn't perfect, right? It's not as nice as it is over here. But Free Surfer does a pretty good job of doing the particle, of generating the white matter and peel surfaces, except for down here. So down here, where you see some signal drop, you'd say, okay, this is a scan that's pretty good. It's going to take some edits, but we'd feel pretty confident it's going to be in good shape. And then if you do those edits, here's what that looks like. So the red here is the same, the original. And then after that, here's the yellow, which is showing that it's extending it out and grabbing these. Okay, and then here's a 4 where this one actually, I'll call this a Suan 4.
Yeah.
Is that fair? This one
It is.
was rated a 4, and the surface was pretty good. Now, one I should point out though on this 4 that this here is a limited. The stuff that's in here is not going to be labeled cortex, and that'll probably just be on a slice or 2, and that's again something very difficult to fix. Okay, so once you decide that it's not a 1, it's not one of these where it's hopeless, it's one of these, then it's time to start editing. And we'll leave it here for today, which is, we say, when we do the editing, we're going to be improving. I mentioned this before, but we don't actually edit the surfaces. We edit those 2 volumes, and then one extra one occasionally, very rarely. The inclusion errors that we saw, where the brain was sneaking outside, the peel surface was sneaking onto non-brain voxels, those are primarily improved by editing the brain mask volume. And exclusion errors, like the ones that we saw here and a little bit here, are the ones that are improved by are corrected by improving the white matter volume. So, and this is, so the next time we meet, we'll go over that more detailed review and edit process. Okay?
Okay.
Okay, and yeah. So I'd hope to get through some of that to give people a chance to look at some brains. We do have the training data sets available, right? So people can do this initial quality control assessment. So what I would do is have them look at have them load each of the scans, and then give each scan a rating.
One rating and then a surface rating.
Okay. There is one problem. I don't know if I can fix it. When I changed the permissions so that you guys could edit them, now no longer we can open them. I don't know how to fix that.
That.
So there's a Boston group and then there's a psych group, and all I've ever been taught to do is, go in and right click on the folder and say permissions, and then I can change the group. But I don't know how to. I thought, because the last group of training, Bobby was able to open stuff and so were the students, but they both just tried and it says permission denied when they tried to open the brain.
Are they in the same group as the other trainees?
Yes, everybody's in psych, as far as I know. So I don't know. Mike did say he changed permissions or whatever, so I don't know what he did.
Yeah, so the thing that change that we had you make, that
didn't work.
But
I couldn't run those commands. It said operation something, so I had to do it manually the way that I just said I.
So you changed the group?
Yeah, but normally that's all I've ever known how to do, and then you were still.
Okay, so you change it to psych?
No, it was. I'm not sure. No,
I would change it back to psych, and then we can work on figuring out what. So I think we are in the psych group, and I think you could be in multiple groups.
Right. Well, that's how it was, but Bobby said she couldn't open them, right?
So what we need to do is change it may just been the command that we sent you. So if we just I would change it back to psych, and then we will change the permissions to add write permission to everyone in the group. So we could do that offline. I can do that even right after this if you want, Emily.
Okay. Yeah, I can change it back to psych, but when I tried to run those commands you sent me, I couldn't do that.
Okay.
I don't know why.
Okay.
MSU people, you guys can go if you need to. I know you have a lab meeting.
So
or not.
You have why don't we do this, Emily? Why don't we you have something there open, but it needs to be Emily logged in order to do it. So why don't we stop this? We've been recording this for posterity, and
yeah.
We'll see if we can make that available to you guys.
Yeah.
Okay. So why don't we we'll stop this meeting, and then let's do another meeting in just a few moments. I'll send you a link to another meeting.
Okay, yeah, I have to go back.
Like.
What?
We could even try Blue Jeans if you'd like.
Oh, yeah. I mean, I don't have a webcam in my office. So, well, I can make it work with a laptop. Yeah.
Okay.
Okay, send me another link. Or I can send you the Blue Jeans one if you want.
Yeah,
okay,
that would be great.
Sounds good.
You can use the one that was in the email. It's always the same.
Okay.
All right, sounds good.
Thank you.
Okay, bye.
Bye.
When you're done with that,
Thanks. It was nice meeting you guys.
thank you.
Meeting you.
Just let me know when I'm out.
Whoa, there's too many things going on. Yes, I would like to leave the meeting.
Can we stop recording? It's over here.